Okay, in this presentation we will discuss about the counters. Basically, counters. What is the working principle of counter? Counter is basically counts numbers. It can be from 0 to upwards direction or upwards direction to downwards direction. According to the counting strategies, the name of the counter is given as up counter or down counter. So first we are discussing about the types of counter. Basically, counter can be classified in two sections. One is called asynchronous counter or ripple counter, and second one is synchronous counter. And for the both cases, asynchronous and synchronous counter is classified into up counter, down counter, and up and down counter or universal counter. In your WBUT question paper, there are some one tricky way questions which is telling you to give the example or give the working principle of universal counter or up and down counter. We will discuss this later on. What is a question comes in that particular year. It is simply the working principle of universal counter, but the way of question comes is a tricky way. Okay, so let us discuss about the synchronous counter and asynchronous counter first. You see, for the case of counter, I have told you in earlier that every time basically flip-flops are used for storing the binary information. It can be either 0 or it can be 1. So using the binary information and using the flip-flops, we are going to construct any counter. It can be up counter or it can be down counter, or it can be up or down counter or modulus counter, whatever. Basically, flip-flops are used as a base parameter or base element to construct any counter. So first we are discussing about the basic difference between asynchronous and synchronous counter. See, first, a counter is basically counts a binary information from upward direction or downward direction. So, and for this counting purpose we are using, say suppose if this is getting very hazy. Yeah, I think you can see it now. Okay, see, if this is the counter, then it takes the inputs and it produces the outputs either in from 0 to say suppose 5 or say suppose 5 to 0. When it is counting from 0 to 5, it is called up, and when it is count from 5 to 0, it is called down. Okay, now inside this counter there are several flip-flops are present which produces the output, and according to the output, each instance of time we can say the counter is going to count 0 or from 0 to 1 or 1 to 2 or 2 to 3, etc. So for this purpose we need flip-flops. So basically what is happened here, flip-flops, there are two inputs. Basically we are using either JK flip-flop or T flip-flop for counter design, because always we are taking the input as high logic. Always the logic for the input will be 1 every time on the initial stage. So if this is your JK flip-flop, so this is J and this is K, and this is the output Q and Q bar. Okay, so this J and this K is always connected to 1. Okay, and here we are using a negative clock pulse. This bubble sign indicate that this is a negative edge triggering clock. That means when the clock, this is the clock, so this flip-flop is going to activate it on only the negative edge of the clock, always on the negative edge of the clock. So initially, so before this negative edge occur, whatever the value of Qn it will remain unchanged. Okay, and then negative clock pulse happens. According to the negative clock pulse, it will goes either from 0 or 1, and it will continues up to the negative again on the negative clock pulse. So every time it is changing its output at the negative edge of the clock. That is why it is called negative edge triggering flip-flop. We are going to use the negative edge triggering flip-flop in case of counter design. Okay. Now for the case of asynchronous counter, basically what is happening, this type of flip-flops is connected in series. You can say connected it in series, and other remaining working principle or other remaining operation I will discuss the later on using an example. So let us go to the example. See, first we see this is an example of 2-bit up counter. This is 2-bit up counter, and it is ripple one. That means this is the asynchronous counter. Okay, now seeing asynchronous counter is basically a counter where the input of the second flip-flop is the output of the first flip-flop. Okay, what is this? I will discuss right now. Okay, now if we are designing 2-bit up counter, then you see it is 2-bit. 2-bit means the required flip-flop is 2. Required flip-flop is 2. Okay, and the number of states, what is states, I will discuss after the end of this asynchronous counter. The number of this, first you write down the formula. State will be 2 to the power of n, and n stands for your bit number. Okay, so here it is 2 to the power of 2. That means total 4 number of states are having for asynchronous 2-bit asynchronous up counter, and the maximum count of this counter will be 2 to the power n minus 1. That means 2-bit up counter can count up to 2 to the power 2 minus 1, that is 3. It can count up to 3. That means from 0 to 3 it will count. This 2-bit up counter is capable to count the information from 0 to 3. Okay, and as I said earlier that we require 2 flip-flop for that. So we are using 2 JK flip-flop. This is the number 1 flip-flop JK, and this is the number 2 flip-flop. Okay, this is also JK flip-flop. We have named the input of this flip-flop as J1, K1, and output as QA and QA bar. Similarly, JB and KB and QB and QB bar. Okay, this is flip-flop number 2 and this is flip-flop number 1. So this is your output QA and this is your output QB. This is your LSB. This QA is your LSB, and this QB is your MSB. This is your MSB. Okay, output bit. So each time this counter, this is entirely it is a counter. Okay, and this counter, each on the negative edge triggering, it will count a value combining this QA and this QB. Okay, now the asynchronous counter, see, in like as I previously told you that always we are using the input, high input state for the input combination. Okay, so J and K for the both flip-flop, it is always connected to logic 1. Okay, now we are using the negative edge triggering clock to the first input. Now first flip-flop, we are using the negative edge triggering clock for the case of first flip-flop. And if this is a asynchronous or a ripple counter, then the output of this flip-flop is considered as the clock of this Okay, that means this QA this QA, this output of this counter is treated as the clock of the next flip-flop. Okay, so if we consider a 3-bit ripple counter, then we require 3 number of flip-flops. Then this QB will also act as the clock of the third flip-flop, right? So this is the main definition of asynchronous counter or ripple counter. That means the output of the previous flip-flop is always taking as the clock input of the next flip-flop. Okay, got it? Now you see, whenever J and K is always 1, then the output, whatever the previous output, it will flip, it will toggle like the truth table of the JK flip-flop. Okay, and this flip-flop is taking this output information as the clock input, right? And also it is taking the input J and K, 1 for each cases. Okay, now if we consider the output first, see, this is your clock, each time it is used the negative edge triggering. So I have make this stage as 1, this as 2, this as 3, and this as 4. Okay, now we are looking at the output, say QA. We are taking this output QA. Now see, when negative, আমি ধরে নিচ্ছি initially QA and QB is initially in 0 state. At the very initial state, that means QN is 0. Okay, now when initially QA is 0, so this is your 0 state. When the negative edge trigger happens, then this inputs previously was 0, so J and K is using the 1 input, right? So according to the truth table of JK flip-flop, it will now changes its state. So if QA was previously 0, then it will change its state and it will become 1 up to the next negative edge triggering. Okay, right? Now again on the negative clock pulse, again QA will fall to 0 because it is toggling in every time. Again it will goes from 0 to 1, and then also it is falls to 0, so it is 1 and it is 0, right? Now we are considering the output for QB, this output QB. Now QB, see, this output of the previous flip-flop, that means QA, is considered as the clock input of this number 2 flip-flop. So instead of using this clock signal, QB or this flip-flop will take the clock input as the QA value, right? So now QB is considered this QA as the clock signal. So what is the negative edge triggering of here? This is negative edge trigger, this is negative edge trigger, right? So if QB is initially 0, if this is initially 0, then it will remain unchanged up to the negative edge trigger of this QA value, because this QB is considering QA as its clock input, and always this is a negative edge triggering, so it will remain unchanged, it will be 0 again. So when the negative edge is triggering, that means whenever QA is equal to QA will fall down, or QA happens the negative edge triggered, then this flip-flop is taking the input as 1, so the previous value of the QB was 0, so it will changes its state and it will become 1 again up to the negative edge trigger, so again it will be false 0. Okay, so this is 1, this is 1, and this is 0 again. Got it? Now consider this case number 1. The value of is 0 0. This is your QB is your MSB, and QA is your LSB. Okay, now this case it is 0 0, this case it is 0 and 1, this case it is 1 and 0, and for this case it is 1 and 1. After this 1 1, it is again becoming 0 and 0. So you see, it is counting from 0 0, then 0 1. That means it is by decimal it is 0, by decimal it is 1, by decimal it is 2, then 3. Then after 3 it will again falls down to 0. That means this is again 0. So if we plot the state diagram, then it will be look like initially it is 0 0, after this it goes to 0 1, then again it is 1 0, and after this it is 1 1, and after 1 1 it will also go to 0 0. So this is your QB and this is your QA. Okay, so if we plot the truth table for this counter, then initially it is 0 0, so decimal value of 0 0 is 0. On the first triggering, QB is 0, QA is 1, so it is 1. On the negative, this second clock negative edge trigger, okay, 1 0, so it is 2, 1 1, so it is 3, and again it is become 0 0, so it is 0. So you can see it is counting from 0 to 3. After 3 it again counts from 0 to 3 as well. So this is your asynchronous 2-bit asynchronous up counter. So if you can make this as your asynchronous 2-bit down counter, then everything will be same, just only the initial state will be only 1. If the initial states will be 1, then this waveform it will just revert on, this will be 1, and after the next clock pulse it will goes to 0, then again 0 continue, then 1, just reverse operation of this. Then you can find that instead of counting from 0 0 0 1 1 0 and 1 1, it will count it from 1 1, then 1 0, then 0 1, and then 0 0. Okay, like the reverse way. So this is up counter, and when it will count from 1 1 to 0 0, it will consider as a down counter. Okay. Now we are coming to the synchronous counter. I hope you can understand the working principle of asynchronous counter or ripple counter. Basically, the output of the previous flip-flop is considered as the input of the next flip-flop. And for the case of synchronous counter, the same thing is happening here also. If this is considered, if this flip-flop is considered, or this flip-flop is using 2 flip-flop, that means definitely it will be a 2-bit counter. Okay, 2-bit. It is definitely a 2-bit counter. So this is a synchronous counter, then you can see on the asynchronous counter, you can see the diagram here, output is using the clock, like the clock of the next flip-flop. But for the case of synchronous counter, a particular clock is applied simultaneously to all the flip-flop connected in a series. If this is 3-bit or 4-bit, then we require another flip-flop here in the series connection. So for each flip-flop, this clock, the negative clock pulse, is triggering at the same time. For the case of asynchronous counter, the output of this flip-flop is considered as the clock. So once it gets its output, this output is considered as the clock. But for this particular synchronous counter, a particular clock is applied to all the flip-flops simultaneously. That means on the negative edge triggering, all the QA, QB and QC having the output value. Okay, now this is synchronous counter, and you can identify a synchronous counter from asynchronous one. Is here for the case of synchronous, the output of this flip-flop is considered as the input of this flip-flop. not the clock, as the input of this flip-flop. So whatever the QA is, it is considered as the input of this flip-flop, and the input of this first flip-flop is considered only as logic 1. Okay, so you can see the difference. For this synchronous counter, only for the first flip-flop the input is considered as logic 1, and once this will give the output, this output is considered as the input of this second flip-flop. Again, if it is 3-bit, then QB is connected as the input for J and K for the third flip-flop. Okay, like the same way a synchronous counter can count from upward direction or from downward direction. Okay, now you see the waveform. Like the previous one, the clock, it is a 2-bit counter, so 2-bit flip-flop is required. Number of state will be 2 to the power n minus 1, that means 3. Okay, n is the number of bit, and maximum count, sorry, this is wrong, number of state will be 2 to the power n, that means it is 4, and maximum count is equal to 2 to the power n minus 1 is equal to 3. Okay, number of state 4 means this is the number of state. Okay, 1 2 3 4. Okay, this is the number of state, and each state we are getting a particular output. It can be from 0 0 0 1 1 0 1 1, etc. Okay, now we consider the first output, QA. Okay, QA, initially if we consider initially QA and QB is equal to 0, then QA is initially 0. Once it's get the negative clock pulse, it goes high, again negative edge, 0, again negative 1, again negative 0. Okay, now we are considering QB. Now we are coming to QB. Now QB, on the previous, for asynchronous counter, see the diagram, QB is taking this QA as the input clock. Okay, but for this case QB will take this clock as its input clock, right? Because clock is acting simultaneously. Okay, now initially QB is initially 0. Now on this falling edge, this QA changes its state, but for at this particular time, before this QA is changing its state from 0 to 1, at that particular time this QB is taking 0 as its input. So here it is now 0. So 0 0 means the JK flip-flop is in memory state, right? So it will continue its state up to 0 to the negative edge triggering. Now when on the numbers 2 stage, when this QA is fall down from 1 to 0, or it is changing its state from 1 to 0, at that particular time this JB is considered as 1. যতক্ষণে এটা 0 তে ফল করে যাচ্ছে তার আগেই এই ইনপুটটা is taken as 1. So when it is 1 1 happens, then this QB is changing the state now. So it is changing the state, right? So it is now 1, and it will continue its state up to the negative edge trigger. Okay. Initially QB is 0. Once the negative edge is triggered, before this QA is changing from 0 to 1, this 0 is taking as the input of this flip-flop, that means J and K is now 0. So once J and K is 0, so this QB will remain unchanged. So when again on the negative clock triggered, when this QA will fall down from 1 to 0 at that particular time, before it falls down to 0, this 1 is taking as the input of this flip-flop J and K. So if this is 1 and 1, then it is considered as, it will change the value, that means 1 1. Again on the negative edge triggered, whenever it is changing the value from 0 to 1, this 0 is considered as the input of this J and K flip-flop. So once it is considered as 0 and 0, so again this will, once it is taken this 0 as the input, okay, then again this 0 is taken here as J and K, so it is 0. So it is now again in memory state. So it will continue its state to 1, and on this negative edge trigger, when it is falling from 1 to 0, that means this 1 is taken here, right? So before it falls down, QA falls down to 0, this 1 is taking as the input for this flip-flop. So 1 and 1 means it is toggle, so it will become 0 again, so it is 0 again, right? So if we consider this state, this is 0 0, this is 0 1, this is 1 1, and this is, sorry, this is 1 0, this is 1 1, and this is 0 0 again. So like the previous one, this synchronous counter is also counting from 0 0 to 1 1. Now if we consider the truth table, then initially 0 0 is 0, 0 1 is 1 on the first negative edge trigger, 1 0 is 2, 1 1 is 3. So repeated time it is counting from 0 to 3 for the key.